Good morning. Now let us see how to find out the resultant vector. Resultant vector of several alternating quantities by using method of components. Let us see one example. Add the following currents as waves and as vectors. I1 is equal to 7 sin omega t, I2 is equal to 10 sin omega t plus pi by 3. Okay. So this is 7 sin omega t, I1, I2 is equal to 10 sin omega t plus pi by 3. This way. Now let us see how to find out this. Okay, so for that, first you find out x component. X component is Im1 sin omega cos omega t cos phi, Im1 cos phi plus Im2 cos phi 2. So I1 is sin omega t, so phi 1 is equal to 0. So 7 into cos 0 plus 10 into cos phi by 3. So 7 plus 10 cos 60, that is 12. Similarly, y component is equal to Im1 sin phi, that is sin 0. Sin 0 is 0, so this is 0. Im2 is 10, sin phi 2 is 60, sin 60. So this is 8.66. So resultant vector is equal to square root of x square plus y square. X component square plus y component square. So in this case it is 14.8 amperes. So it comes around, it is 14.8 amperes. Alpha is equal to tan inverse y by x. Y component is 8.66 and x component is 12. So 35.8. Hence the resultant equation can be written as IR is equal to 14.8 sin omega t plus 35.8. And this is the representation. Okay. Number. Nice. Now to this problem. Circuit consists of four loads in series. The voltage across these loads are given by the following relations measured in volts. V1 is equal to 50 sin omega t. V2 is equal to 25 sin omega t plus 60. V3 is equal to 40 cos omega t. V4 is equal to 30 sin omega t minus 45. Calculate the supply voltage giving the relation in similar form. Now phasors representing the maximum values of four voltages are shown in the figure. Okay, V1 is 50 sin omega t. Okay, 50. So this is V1, 50 sin omega t. V2 is 25 sin omega t plus 60. V2 and V3 is 40 sin omega t plus 90. So this is V3, this is V4. Okay. Now V3 is 40 cos omega t, that can be written as 40 sin omega t plus 90. Now let us find out the x component. X component is 50 cos 0, that is Im1 cos phi 1 plus Im2 cos phi 2, 25 cos 60 plus 40 cos 60 plus 30 cos 45. That is 50 plus 12.5 plus 0 plus 21.21. 21 is equal to 83.71 x component. And y component is Im1 sin phi 1 plus Im2 sin phi 2 plus Im3 sin phi 3 plus Im1 sin phi 4. Okay. So 50 sin 0 plus 25 sin 60 plus 40 sin 90 plus 30 sin minus 45. That is minus 30 sin 45. So this will become 40.44. So x component is 83.74, y component is 40.44. So the resultant is square root of x square plus y square. So that is 93 volts, and tan phi is 40.44, y component by x component 0.483. So phi is equal to tan inverse of 0.483, which is 25.8 degrees. The equation of the supply voltage is 93 sin omega t plus 25.8 degrees. Okay. This is 93. Not true. Next. 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 Resistors. Resistance is the property which opposes the flow of electric current. A passive component that offers resistance is known as resistor. This is the symbol for the resistor, and the units are ohms and is represented by the symbol ohms. This one is ohm symbol. According to the Ohm's law, the ratio of the applied voltage to the current flowing through the conductor is known as resistance. R is equal to V by. This is classification of the resistors. So fixed resistors and variable resistors, and fixed resistors are classified into carbon resistors, wire wound resistors, metal film resistors. Again, carbon resistors are classified into carbon composition, cracked carbon. Okay, next wire one, power type, precision type, metal film, thin film and thick film. Variable resistors, potentiometers, and again potentiometers are carbon and wire one. And variable resistors are classified into rheostats, decay resistance box, thermistor, varistors, light dependent resistor, trimmer. This is about the classification of the resistors. Now let us see the specification of the resistors. So first specification is resistance value. This is the value of the resistance expressed in ohms. Its typical value is ranging from 1 ohm to several mega ohms. It is either printed on the body of the resistor or indicated by color code. Depends on the structure. Okay, tolerance. Tolerance is the variation in value of the resistance that is expected from the exact indicated value. That is the value printed on the resistor or indicated by the color code. Indicated value, it is the variation of the value of the resistance that is expected from the exact indicated value. Usually tolerance is represented in percentage, typical values ranging from plus or minus 1% to plus or minus 20%. Power rating. This is maximum amount of heat in watts that can be dissipated by a resistor without destroying the resistor or without causing any damage to it. Okay, choice of power rating of resistor is important before using the resistor in any application. The power rating of the resistor should be decided based on the maximum current that flows through the resistor in the circuit. Typical values of power ratings are 0.1 watts to hundreds of watts. Temperature coefficient of resistance. It gives the variation of resistance with the change in temperature. Variation of resistance with change in temperature. It is usually measured with reference to the resistance at 25 degrees centigrade. Voltage coefficient is measured as a change of resistance of the resistor with change in the applied voltage. That is operating temperature, last one. The temperature range over which the resistance is fairly constant. Sixth one, that is. Next, frequency response. The resistance of a resistor varies with frequency. At low frequencies, the value is equal to the DC resistance. But as frequency increases, the resistance decreases due to the phenomena called Boyle effect. As the frequency increases, the resistance decreases. The frequency response is the graph drawn between the frequency on x-axis and resistance of the resistor taken on y-axis. It is particularly important when resistor is used in high frequency applications. Okay. Not bad. Next, this precision E, not O. Next. Next, preferred values. What is preferred values? Okay, what is a necessity? The Electronic Industries Association and other authorities specifies standard values for resistors. Okay, sometimes referred to as the preferred value system. It's not possible to manufacture all values of resistors starting from 1 ohm to 2 megavolts. For uniformity of production, only particular values of resistors in each tolerance range are manufactured. These set of values are known as preferred values. The usual specified tolerances are 5%, 10%, and 20% for the ordinary resistors, while precision resistors may have selected tolerances as plus or minus 1%. The preferred values for different tolerances are given below. So 5% tolerance, these are the values. 10%, 10, 12, 15, 18, etc. 20% tolerance, these are the values. Noted. Next. Next. Classification of resistors based on composition. Carbon film resistors, metal film, metal oxide, wire bond resistors, precision resistors. Okay. Carbon film resistors and carbon composition resistors. Carbon composition resistors are made of finely divided carbon or graphite mixed with a powdered insulating material as a binder. In the proportions for the desired resistance value. Carbon composition resistors are made of finely divided carbon or graphite mixed with a powdered insulating material as a binder in the proportions for the desired resistance value. Resistance range 2 ohms to 20 megaohms. Tolerance is plus or minus 5%, plus or minus 10%. Overrating 1 by 8 watts to 1 by 8 watts to 2 watts. Working voltage range 125 volts to 800 volts. These are the specifications of carbon composition resistors. Carbon film resistors. These are made of depositing carbon film on ceramic rods. Okay. Different resistance values are obtained by varying thickness of the carbon film. Resistance range is 1 ohm to 1 mega ohm. Tolerance is plus or minus 1% to plus or minus 5%. Overrating 5 volts. Working voltage 500 volts. Mixed metal film resistors. Instead of carbon, a thin layer of film or film of metal or metal oxide or metal alloy is coated on a glass or ceramic substrate. Okay. Resistance metal film resistors. A thin layer of metal or metal oxide or metal alloy is coated on a glass or ceramic substrate. Resistance range is 0.5 to 10 kilo ohm. Tolerance is plus or minus 2 to plus or minus 3%. Operating 5 hours. Working voltage 300. Commonly used materials for making metal film are nickel chromium film, that is metal alloy, and tin oxide film, metal oxide. Depending on thickness of the film, the metal film resistors are classified as thick film resistor, that is film thickness is more than 1 millionth of an inch. Thick film types are either cylindrical rods or flats. Thin film resistor, metal film resistor, film thickness is less than 1 millionth of an inch. Thick films have a greater physical strength. Metal oxide resistors, they consist of oxides of tin and antimony. These oxides are fused onto a glass or ceramic substrate. Okay. This oxide layer varies in thickness, which are hard and stable for long time use. Resistance range is 1 kilo ohm to 10 giga ohms. Tolerance plus or minus 0.5% to plus or minus 5%. Power rating 500 milliwatts. Working voltage 350 watts. Precision resistor, where the highest accuracy is required. Where the highest accuracy is required. With a good stability, precision type resistors are used. These are the types that are incorporated in high-grade multimeters. A precision resistor is a resistor that is a very low tolerance value, that is plus or minus 0.1%. Precision type wiring resistors are available in the range of fraction of ohm to 10 mega ohm with a power rating of the order of 2 watts. Resistance range is fraction of ohm to 10 mega ohm. Power rating is 60 watts may exceed 300 watts in special cases. Tolerance plus or minus 0.1%. Operating temperature 55 degrees centigrade to 365 degrees. Temperature coefficient 50 to 250 ppm per degree centigrade. And working voltage is 500 volts. Now you can note down. Next. Next. Open film resistors. Next. Okay, we'll continue in the next lesson.